Here we're going to see a very interesting application of tensile strength and compressive strength and tensile stress and compressive stress. So going back to the concept, here we have a beam. Let's say the beam is suspended at both ends, and beams are usually used to hold big loads so that we could put forces on them. And so let's say we apply a force to the beam, and if the force is very large, typically the beam will be as a response, will begin to sag to some extent. Of course, I exaggerated the sag so we can see what happens. But what the result is that the atoms near the top of the beam get pushed together, and so there is a compression taking place near the top of the beam. On the other hand, on the far end of the beam, from where the force applies at the bottom end of the beam, the belly of the beam, so to speak, that part of the beam is under tension, meaning the molecules are being pulled apart. And of course, the danger is that if you apply too much force, the beam could actually begin to crack. So for example, you have a wooden beam, you apply too much force, you can actually destroy the beam. And of course, that's the purpose of the beam, is to hold a lot of weight. But if the beam starts cracking, of course, it doesn't do what it's supposed to do. So what people started realizing is that, wow, what's really the part of the beam that's really under compression and under the most compression is the top portion of the beam right here. So what I did over here is just kind of mark that off. It's this portion of the beam that's going to be under the most compression. The most force is applied to the beam, pushing the molecules together. And the bottom end of the beam is going to be under the most tension. Because of the sag of the beam, the molecules are going to be pulled apart the most at the very bottom of the beam. So those are the two portions of the beam that are the most important, and the portion in the middle is not near as important for the strength of the beam. So therefore, we build what we call the I-beam. Beams that have a very wide section at the top, which is not necessarily very thick, but very wide. Then we have a single, very thin portion going down, and then we have a second portion right here, which is the bottom end, again, that is very wide, not necessarily very thick. And so what happens then is that portion now, as you put force on the beam, and you could put a lot of force on the beam right here, then this is going to be again under compression. As the beam sags, those molecules are going to be pushed together. But since there's such a large cross-sectional area, that causes therefore the ability to absorb a lot of force. So the stress will be reduced simply by the fact they have a much larger cross-sectional area here than you do over there in that part of the beam. And then likewise at the bottom of the beam, by pushing down on it, those will be under tension. Those molecules are going to be pulled apart. But again, since it's a much larger cross-sectional area, the stress will be reduced because the A is much bigger than that. So we have a much smaller stress on an I-beam compared to a typical beam like that that's built like a normal beam. Now, also, this portion, the wider you make this, it has some benefits as well. But the key areas of defense against stress from putting weight on a beam are the top and the bottom portions. So what that means is if you reduce the stress, that will then cause to have less strain as well, because the ratio of these two will always equal to what we call Young's modulus, which is dependent on the property of the material. So if we make a steel beam that has a very large Young's modulus, if we reduce the stress, we will then reduce the strain as well, and it will not sag as much. So if you want a very strong structure, instead of using beams that look like this, you're going to use I-beams, and you have a lot less strain, a lot less sag when you put weight on it, and a lot less opportunity for things to break, so they're much stronger, and that's why you use the I-beam. So a nice application for stress and strain, and how we found a way to get around the problems of beams breaking if we put too much force on them.